Hola a todos,
Hola a todos.
bienvenidos a la primera edición online de Kaggle Days Meetup Spain. Hello everyone, welcome to our first online Kaggle Days Meetup Spain. Estamos muy contentos de retomar los Kaggle Days Meetup y de contar con vuestra presencia en esta ocasión en versión online. El evento de hoy será mixto en idiomas. Tendremos partes en inglés, partes en español, pero contaremos con subtítulos en español e inglés para que sea más fácil seguirnos. Permitidnos decir esto mismo para la audiencia de habla inglesa. Today's event will be in mixed languages. We will have parts in English and parts in Spanish, but we will have subtitles in both Spanish and English to make it easier to follow.
Bueno, para los que no nos conozcáis, contaros que este es nuestro sexto Kaggle Days Meetup. Hemos organizado ya 5 eventos presenciales sobre competiciones de Machine Learning en Kaggle, tanto en Madrid como en Sevilla. Y hoy estrenamos nuestro primer evento online. Para los que estéis interesados, podéis ver los vídeos de nuestras anteriores charlas en YouTube, donde tuvimos grandes maestros de Kaggle como invitados. José Antonio Guerrero fue nuestro primer invitado y fue número 1 en el ranking global de Kaggle y nos dio 2 charlas, una sobre cómo llegar a ser número 1 en Kaggle y otra sobre el uso de gradient boosting con una respuesta multivariable. En el segundo meetup tuvimos a Pavel Jankovic, que nos habló sobre la preparación y validación de datos temporales. En el tercer meetup tuvimos a Alberto Danese, que nos habló sobre cómo funciona realmente gradient boosting. Y en el cuarto y quinto meetup tuvimos a Gilberto Titerix, quien ha sido el número 1 que más tiempo ha estado en esta posición en Kaggle y que nos dio 2 charlas, una sobre los retos en la automatización de Machine Learning y otra sobre consejos para la ingeniería y selección de variables. Comentaros un poco la agenda del evento de hoy, que será la siguiente. Comenzaremos con la entrevista al ponente, a Yauhen Babakhin, gran maestro de competiciones de Kaggle. Continuaremos con la ponencia sobre Deepfakes por Yauhen. Después volveremos a la reunión de Zoom para las preguntas y respuestas que contestará Yauhen en directo. Y por último, jugaremos a un Kahoot de Machine Learning para divertirnos y dar un premio al ganador.
El tema de hoy, como os habíamos adelantado, tratará sobre los deepfakes, cómo se generan y cómo se detectan utilizando inteligencia artificial. Creo que a día de hoy todos conocemos qué es un deepfake. Es una tecnología que se está utilizando, que utiliza redes neuronales para hacer face swap. Esto es, sustituir el rostro de una persona por el de otra en un vídeo. Y esta tecnología está al alcance casi de cualquier bolsillo y permite obtener resultados bastante creíbles. Hace poco Cruzcampo lanzó un anuncio de televisión en el que revivía al artista Lola Flores. Y el Museo Dalí de Florida publicó un vídeo donde nos trajo al artista del siglo XX de vuelta a la vida. Y también muchos habréis visto que el vídeo que ha sido viral el día después de las elecciones generales, donde podíamos ver una secuencia del equipo A en la que se habían cambiado la cara de los personajes de la serie por los líderes de los partidos políticos, ¿no?, de aquellas elecciones, ¿no? Creo que todos estos vídeos pueden ayudarnos a comprender que lo que veamos a partir de ahora puede ser cierto o puede ser una suplantación. O una suplantación de la voz y de la imagen de la persona que estamos viendo. Entonces creo que aparte de estas representaciones artísticas es mucho más preocupante los posibles usos que se pueden hacer de esta tecnología suplantando la identidad de otra persona. Facebook ha empezado a retirar vídeos donde se usa esta tecnología y ha actualizado las reglas de uso y permite casos marginales como sátiras y esto no acaba más que de empezar. ¿Qué calidad van a tener estos deepfakes dentro de unos años? ¿Vamos a ser capaces de distinguir un vídeo real de uno falso? Y aquí es donde entra la automatización de detección de deepfakes con inteligencia artificial.
Bueno, y para hablarnos de deepfakes, hoy tenemos un ponente de primer nivel, a Yauhen Babakhin, gran maestro en competiciones de Kaggle, y que quedó en las primeras posiciones obteniendo una medalla de oro en la competición de Deepfake Detection Challenge que organizaron hace un año, entre otros Amazon, Facebook y Microsoft en la plataforma de Kaggle. Yauhen tiene una titulación de máster en análisis de datos aplicado por la Universidad Estatal de Bielorrusia. Tiene más de 5 años de experiencia laboral en ciencia de datos, habiendo trabajado como científico de datos en distintas compañías y actualmente Yauhen trabaja como Senior Data Scientist en H2O y está focalizado en los modelos de AutoML en el área de visión artificial. Es también el primer gran maestro en competiciones de Kaggle de Bielorrusia, con medallas de oro tanto en competiciones de Machine Learning clásico como de Deep Learning. Para dar visibilidad al evento y agradecer a Yauhen su participación, nos agradeceríamos que compartierais comentarios y capturas de pantallas en las redes sociales con el hashtag Kaggle Days Meetup Spain. Y bueno, con todo esto creo que es un buen momento para que pasemos a la entrevista con Yauhen y lo conozcamos algo mejor a él y su camino a gran maestro en competiciones de Kaggle. Hello, Yauhen. It's a pleasure for us to have you in our first Kaggle Days Meetup Spain. Thank you for coming.
Yes, thank you for inviting me. Yes, thank you. I'm happy to be here.
Thank you, Yauhen.
Before we start with your presentation about deepfakes, we'd like to know a little bit more about you and about your path to Kaggle Competition Grandmaster. So could you tell us a little bit about yourself? What is your background? How did you get interested in machine learning?
So basically I have my bachelor in applied mathematics. So I started as a mathematician, and my major was like economics. So I was gonna to become like to work in the economics sector. But fortunately, I started to work pretty early, and like during my university studies, I've had experience in the banking domain. So I have worked in a bank. And I've quickly realized that it is not what I want to do like during my whole life. And yeah, it like allowed me to switch the careers. And yeah, like I've entered master's degree in applied data analytics. And yeah, and the reason for that was that someone just at the university, my group mate said that, did you hear about this term data science? So it seems like a pretty cool thing to do. And it was, I guess, back in 2015, maybe something like this. So yeah, and I've started to read about it, to watch different posts, videos, yeah, and I quitted my job in a bank, yeah, and devoted all my time to work on data science.
Wow, really interesting.
Yauhen, how did you improve your skills in machine learning? Any recommendation to our audience?
So basically, like since the beginning of my career, I guess that Kaggle was and is still my main source of like improving my skills, like machine learning skills. And I think that like the main component is practice. So like unless you're trying something by your hands, and unless you try to implement something or run some experiment, like reading and like watching the videos is not really helpful until you try it. So from my point of view, it should be a combination. So if you have read something interesting, or if you just notice some approach, and maybe there is already some code implemented, but it is better to like run it yourself instead of maybe just reading and skimming, because when you have like something like, okay, I understand this, then probably it means that you didn't understand anything until you have implemented it. And so, and for me, probably Kaggle is still the main source of knowledge. So like I still go there for some new Kaggle, like for some new problem types, for some new data sets. Yeah, and it helps me a lot.
What skills would you say are the main ones to achieve a good level in applied machine learning?
I think that here we should probably separate like two different areas of machine learning, right? So if it is like kind of research machine learning, so if you're working in some research company or like research department in your company, then probably like the machine learning specialist should kind of be up to date with all the recent papers, and he should be kind of like capable for implementing any paper and any new approach. And yeah, and it is kind of like one set of skills. But if we are talking about some engineering machine learning, then probably the best skill you should have is writing a code. So writing like clean and understandable code. So just like at least a Python code. And I think like from my like perspective and from what I see right now, it is the main skill, and I still like I'm lacking it. So I'm always trying to improve my coding skills. And yes, so now I guess there is a focus like in all the like libraries and open source projects that everything is mostly available, right? So you don't need, so if your goal is to run some experiment on some data set, then most probably there is already a lot of like open source libraries that you could use. And it is just a couple of lines of code to implement it. So it is not anymore so fancy to run like all the known problems. And that is why like the major skill should be like writing clean code, and that is understandable to others probably.
And what do you do to stay updated with all these advances in machine learning?
Yeah, right. It is pretty tricky right now. So it is very hard to be up to date and to follow all the new papers, resources, courses, and I don't know, lots of resources. And probably the major source for information for me is open data science community. I don't know, have you heard about it? So it is like it started as a Russian-speaking community of data scientists, but now it is kind of becoming global. So there are, I guess, around 40,000 people already. So it is pretty large community, and it is it is a Slack channel with lots of different like topical channels. And basically, if something new is popping up in the area of machine learning, then it will appear in this Slack channel, like, I don't know, in a half an hour. So there are at least one person from this 40,000 people who is following something, and it is appearing there. And I mean, like, probably it is their, so it shows me their latest trends in machine learning. But still, like now, I'm mostly working with computer vision in my job. And even like following the whole computer vision area is impossible right now. So I mean, like if you're working only on image classification or image segmentation, then it is impossible to follow like object detection, for example. So in this case, I try, if I'm kind of working on some specific problem type, then I'm trying to read everything about this topic. But at some point, if I need it again, then I needed to reread everything because it is impossible to remember everything. So.
Okay, yeah, it's really difficult to be up to date. And talking about Kaggle and your path to Kaggle Grandmaster, how and when did you start competing on Kaggle, and how were your beginnings?
Yes, so basically, as I said, my whole career path is connected with Kaggle, so it is a nice friend like in my machine learning world, and I've started like data science learning as at EDX, so it is a learning platform with online courses, and there was a course called Analytics Edge, I guess, and there was some theory, and one of the like practical exercises there was a Kaggle competition, specifically for the participants of this course. So it was just a closed competition, only for the participants. But at that point, there were already some proficient users in this course, and it was a bit demotivating that they were like beating like us who just started learning data science. And it was, for me, it was super fun experience. So I mean, like probably it is not for everyone, that because someone like I've heard a lot of things about Kaggle that it is kind of demotivating. So when you can't go like to the top of the leaderboard, you kind of like you're starting to be demotivated, and it is hard to keep up with this. But for me, like this competitive environment is like what I want. So I want to be at the top of the leaderboard, and for this purpose, I need to read, to learn a lot. And it was exactly what I was doing during this first like playground competition during this course. And I was pretty good at the public leaderboard. So I guess at the public leaderboard, I was about top 30 maybe, and I was super happy with the results. And of course, I haven't known anything about the private leaderboard and what could be the surprises there. And then like the next day, I've opened the leaderboard and I found myself like, I don't know, maybe at 400 position, something like this. And it was like a big surprise for me. Yeah, and it was like, again, it was super demotivating, right? So you're kind of losing and everyone is on top. But like my first reaction was, of course, like this disappointment. But afterwards, I started to read and go through the forum and just to find out the reason. What was the reason why like my performance was so bad on the private leaderboard? Yeah, and like it was the major lessons that probably you need a good cross-validation strategy, local cross-validation strategy before running any Kaggle competition. So yeah, so it was not very pleasant experience, but it was like a kind of trigger to give me a push to learn more about machine learning.
Well, and can you tell me us a little bit, how do you usually approach a Kaggle competition? Do you usually follow a common routine? Does it depend on the type of problem?
So basically, I don't have any like strict pipeline of how I'm approaching the competitions. But yeah, but the steps are basically I'm starting with like working on the new Kaggle competition like alone. So I do not read any like discussions or like kernels or code that participants are sharing, in order to like kind of make my own impression about the dataset, to learn something from dataset and maybe generate some ideas. And I'm working like alone until like I have some pipeline, like end-to-end pipeline from training to the submission. And if I submit and everything works, then yes, then at this point I'm starting looking at the forums or at the code to kind of get more ideas. And like once your pipeline is kind of established, I guess it is the easiest part in the competition, when you just try to implement new ideas and maybe tune some hyperparameters and train more models. So it is much easier once you have this pipeline. And I'm also like, during the competition, I'm always tracking the forum all the time. So like each day or like each 2 days, I'm going through all the new messages in the forum and trying to be up to date of what people are doing, what people are trying. And yeah, and in some cases, it is very kind of very beneficial, because like you're always up to date with the competition, and you could try ideas a little bit like earlier than others. Yeah, and probably I'm not the like kind of person who starts competition like in 2 weeks and then wins a gold medal. So for me, it is better to start early and yeah, and have this like kind of background of time and try more ideas, and yeah, maybe like move slowly. But yeah, and speaking about different problem types and different competitions, I would say that for specifically for the deep learning competitions and maybe images and more NLP also competitions right now, like the problem is that their experiments, like experiment loop, is very slow. So if you want to try some new feature, some new idea, then in tabular competitions previously it was running like in a couple of minutes, right, or like in an hour, and you could try like a dozen of ideas during the day. But now for the deep learning competitions, just changing one thing and rerunning the model could take like 1 or 2 days to train the model, and that is why it is not so fun for me. So, and it is hard to try like a lot of ideas, and that is why you need to be kind of careful in this selection process. So when you are trying to get new ideas, you need to be careful selecting it and spending time only on some like, maybe like that will give you the best score improvement. Yeah, so that's it probably. Okay, probably we can't.
No, we can hear you, Virilo.
Thank you. And how much time do you spend in a Kaggle competition, especially in those ones in which you achieved a gold medal?
Yeah, it depends. So again, it depends on the like, is this competition is interesting for me, or is it just like run some like pipelines in the background? But usually, like speaking of time, probably I have like two major phases of kind of I mean like active and not very active phases in the competition. So when I'm implementing the first pipeline, the first baseline to submit, then it is super active, and you need to invest a lot of time. And afterwards, once it is there, you could just tweak experiments, try other ideas, and it is not so time consuming. And also probably during the last week, I'm also spending a lot of time to like try all the like last hour ideas and last day ideas. And probably like during these active phases, I could spend like about like 1 to 2 hours each working day, like in the evening, working on the competitions, and maybe about like 4 hours during the weekend to implement new ideas. So basically during the weekdays, I'm running experiments, trying some smaller ideas that are kind of fast to implement, and during the weekends, I'm trying to work on like larger ideas. And during the active phase of the competition, yeah, probably I could spend the whole weekend so working only on Kaggle, so just the whole 2 days. So it is not a very healthy probably, but yeah, but when it is fun, it is super cool to work on the competitions. Yeah, and at the same time you could just work during the weekdays also up to like late night if you have some interesting ideas. So it really depends. But if I'm actually participating and if I want to achieve a gold medal, like I'm trying to try at least one experiment each day. So at least to have a single bit of information each day.
Nice. So you have to invest time. It is clear. It requires an effort. And do you use a framework for deep learning like Fast AI, PyTorch Lightning, Catalyst, or Ignite for Kaggle competitions?
Yeah, so basically, like for the majority of my like deep learning competitions, firstly, I've started to participate in deep learning competitions like using Keras, and it was kind of also like a framework on top of TensorFlow, so it was easier for me to learn and use it. And for like currently, I'm using PyTorch, and I've tried like a couple of different like projects, and yeah, a couple of from ones that you have named. And like I have selected like PyTorch Lightning for me. So like for me, it was like the best choice probably. Like, I mean, from the functionality and from the flexibility. And I guess all my like good solutions and all my like open source code is written in PyTorch Lightning. However, like recently, I observe that sometimes it is not flexible enough. So I mean, like probably my skills are growing, and I want to try like more stuff and like to go deeper in the PyTorch itself. And so like recently, I'm using like pure PyTorch. So I'm trying to rework my pipelines, not to use any of these like frameworks, and try to have my own like framework that is suitable for me, that is like flexible enough. And yeah, so I'm working on something like this right now.
Cool. And another question, Yauhen. Training properly a neural network involves a lot of tasks, like choosing the network architecture or modifying an existing one, hyperparameter tuning, preprocessing, use of external data. If you had to choose just one or two, what do you think are the most important ones? In which tasks do you spend the most time?
Yeah, you're right. So basically, like if you're training any deep learning model now, you have like really like dozens and hundreds of hyperparameters that you could tune. And the problem is that they are not independent, right? So if you're changing some parameter, you probably need to change like 10 others in order to achieve the same quality of the model, for example. But if I would select two of them, then probably like the most important one probably is architecture itself. So I mean, like even if it is not something specific, but if you are just training some image classification model or like text classification, and all the architectures are known, still it is really surprising to see that for particular data sets, some architectures are working like much better than the others. So and this kind of like difference is kind of like they're like from another league. So it means that there's like you can't achieve this difference in performance with changing like optimizers or changing like augmentations in the images or something others. So probably like I'm starting firstly with architectures. So I'm fixing all the other hyperparameters and trying to find the best architectures that works for this data set. But the tricky thing that the most like second most important hyperparameters is probably learning rate. And for different architectures, you need to specify different learning rates, because like all these like pre-trained models have already been using some like specific learning rate during the pre-training phase. And that is why like they could like converge slower if the learning rate is too small, or if learning rate is too large, then they just start diverging. And that is why like I'm trying to tweak it in a combination. So if I change the architecture, then I have a grid of possible learning rate values, and I try to also adjust them. And like I'm keeping all the other hyperparameters fixed, and only afterwards, once I have selected the best like architecture, the best learning rate, then I'm working on other hyperparameters that usually bring like also brings some value, but like on a lower margin than the architecture and learning rate.
One last question. Could you tell us some general recommendation for those who want to improve on machine learning competitions? Some tricks and something to focus?
Yeah, probably the best trick is that you need to devote a lot of time to the competitions. So like from my point of view, like your rank on the leaderboard is how much time you have spent in the competition. So the more you spend, the better probably your rank will be in the end. And like from this perspective, probably the best advice is you need to be like consistent working on the competition. So if you have started working on something, then probably like try to push to the end, because I know a lot of people who are starting the competitions, and then they implement some baseline. So they have basically made their hardest part in the competition, and afterwards they are seeing themselves like at the bottom of the leaderboard, and maybe like even worse than some public kernels. And it is kind of like when there are like 1,000 people before you on the leaderboard, they just start to quit the competitions and saying, okay, I will try another one, and they just jumping from competition to competition, and basically they do not achieve any success. And like from my point of view, like you need to set the goal for the competition, and it should be like probably the knowledge. So I guess it is not about the medals, right? It is all about the knowledge. And once you have it, then you have this kind of like intent. Even if you're at the bottom of the leaderboard, you will go through the like public kernels. You could see what you're doing wrong, maybe, or what you could like take some ideas maybe from the public kernel, or you could just like maybe blend public kernel and your current solution, and you will jump like at the top of the leaderboard. And then it's kind of like giving you a second breath. So once you are kind of like overcame this like public kernels like baseline, then you kind of like feeling better, right? And you could try more ideas. So probably like my major like advice is to try to be consistent and try to work hard until the end of the competition.
Thank you very much, Yauhen. I think it has been very inspiring for all of us. Let's now turn to this interesting presentation of deepfakes.
Thank you, Varila. Thank you, Javier. Hello, everyone. It is a pleasure to be here to be a part of this Kaggle Days Meetup. And today I will be talking about the deepfakes from generation to detection. So a couple of words about me. I'm a Kaggle Competitions Grandmaster, and I have gold medals in different problem types, including tabular data competition, NLP, and computer vision. Originally, I'm from Minsk, Belarus, but now I live in the Czech Republic, and I work as a senior data scientist at H2O.ai. So to begin with, let's consider the agenda for today. We'll firstly start with a definition of what actually deepfake is, then we will consider some methods for deepfake generation, and then we will talk about the deepfakes detection methods. And afterwards, in the end, we will talk about the Kaggle Deepfake Detection Challenge. So let's start with the definition of a deepfake. Probably all of you have heard about the deep learning term. So it is an area of machine learning that specifically deal with artificial neural networks. And the term deep here means that we are using the deeper networks with additional hidden layers. And the deepfake is a combination of these two words, deep learning and fake. The idea here is under deepfake, we usually mean some synthetic media when we are trying to substitute one person in image or video with another identity. And for substituting, for generating such fakes, we are using the deep learning methods. And that is why it is called deepfake. Probably deepfake is the most well-known application of deep learning in the global world. I mean, outside of the deep learning community, because it is widely used in different entertainment applications and has appeared in a lot of different medias and shows. However, the term has evolved pretty recently, and according to the Google Trends, the first mention of the deepfake has appeared only in the beginning of 2018. And since then, the interest to this topic is steadily growing. And the same pattern holds for their number of papers. So here is a plot of the papers that are mentioned in deepfake term in the last 5 years. And as you can see here on this plot, the first paper started to appear also only in 2018. But afterwards, there was a huge growth of interest in this topic. And it seems that in 2021, this growth is slowing down. However, this area is still a very hot topic in academia. All right, so there are a lot of different deepfake types, and on this slide we will cover 4 of them. The first here at the top left is a so-called entire face synthesis. So in this case, we are generating the completely new faces that are not exist in the real world. Another approach is attribute manipulation. It is at the top right. In this case, we have some real faces, and we just manipulate some attributes on these faces. So we could, for example, change the haircut or add glasses to the original image. And the other 2 methods at the bottom actually require 2 persons, the source and the target. In the identity swap, the source could be a video or image, and in this case, we're completely substitute their whole identity on this video or image, and we obtain a new video or image with a completely another person. In another approach, in the expression swap, that is at the bottom right, we again have some initial source video or image, and we do not change the identity of this person, but we take the expression from some target, from another person, that is called target, and afterwards we apply this facial expression to the original image or original video, and we're obtaining the new type of the deepfake. So here on the slide, you could see the examples, different examples of the deepfake. At the top left is a Jim Carrey on the left. It is a deepfake of the original Jack Nicholson on the right. And as you could see, it is a complete face swap where we have a complete substitute of the identity in the video. And this deepfake has a pretty good quality. And at the bottom right, we have 2 rows. In the first row, we have a fixed identities of some people, and at the second row we animate them with some target person from the video, and in this case we're applying the facial expression. So we're changing the static images to use their facial expressions from their input video. So all in all, there are different pros and cons of the deepfakes. So the positive side of this technology is that it could be used for different entertainment applications. And as a consequence, it could also be used for promoting the deep learning research among the general audience. However, the drawbacks of this approach of the deepfake generation is that it could be used for some bad and dangerous applications, for example, for fake news generation or for some different fraud activities. And that is why we need some reliable methods to distinguish between real and fake content. But before we talk about how we could detect whether their content is fake or not, we'll talk about the methods that are used to generate the deepfakes. Generally, there are 2 families of the methods that are used to generate the deepfakes. There are autoencoders and generative adversarial networks that are also called GANs. In this section, we'll briefly talk about both of these architectures, and then we will see how they could be applied to generate the deepfakes. So autoencoders is the architecture that consists of 2 parts, the encoder and decoder. We have some input that is in blue color here, and this input is passed through the encoder neural network, obtaining some representation. Usually this representation has a lower dimensionality than the original data. And we kind of projecting the input data to some encoded space, and this space is also called latent space. Afterwards, we take this vector from the latent space and pass it through the decoder part of the network, obtaining and trying to reproduce the initial data set. So in this case, the goal of this network and the loss that we're trying to optimize is to minimize their decoding error, and we'd like this output to be as much similar as was the input. And having trained this model, we are obtaining the architecture that allows us to firstly pass the input data and obtain some latent representation, and then decode it back to the initial data. And these autoencoders could be used for generating the deepfakes. In this case, we need 2 persons, and for each of the persons, we need a set of the images to train the model. So the prerequisite here is that we need images for both of the persons. Afterwards, we train a usual autoencoder, but the difference here is that we have a common encoder for both people, for in this case face A and face B. We're obtaining some latent representation of both faces, and the idea of using the shared encoder is that now these faces are in the same latent space. So basically, we are projecting the both identities, both persons, into a single latent space. But afterwards, we're using a separate decoder for each of the persons. So in order to go back to the original image to reconstruct it, we're using the separate encoders for each of the persons. Having trained such model, we now could swap the decoders and use it for the generation. So for example, we have this original person A, we pass it through the common encoder, we obtain the latent representation of this person A, and afterwards we apply the decoder from person B. And as a result, we are obtaining all the facial expressions from the person A, from the original image. However, the face now is from the person B, because we were using the decoder B to reconstruct it. And this approach is widely used for generating the deepfakes, and one of the most popular libraries that are available online, available in this GitHub repository that is mentioned here at the bottom of the slide. It is also using this autoencoders approach. Another family of the approaches is based on the generative adversarial networks. And GANs is kind of the model that trains 2 models simultaneously. So it trains the generator and discriminator. Generator tries to generate some data that is similar to the real data, but it is fake data. And the discriminator tries to distinguish whether it is a real or fake sample that is coming to it. And together, we're kind of optimizing here the minimax problem when generator tries to fool the discriminator and tries to maximize its error, where discriminator, on the contrary, tries to minimize its error and try to distinguish between real and fake samples. And there are different ways to apply GANs for the deepfake generation. Today we will be talking only about a single approach that is called neural token head. And again, the link to the paper is here at the bottom of the slide. And basically the idea of this approach is that we first train some meta model, and this meta model is usually trained on a very large data set. Firstly, we are passing to the network the input images together with its face landmarks, and we pass it through some embedder that allows us to generate the embedding representation of the input face. Then this embedding representation is projected to the generator to initialize the weights of the generator. And the generator itself uses only the landmarks as an input. And afterwards, using these landmarks, it tries to generate the real face, like the real photo of the person, the real image. And the discriminator in this case is kind of, as usual, tries to distinguish between the generated face and the real face. And having trained such meta model on a large data set, afterwards, if we have a new person that we want to generate a deepfake for, we just need to fine-tune this model on the new person. And if you recall, for the autoencoders, we need 2 sets of images for each of the persons. So it means that to train such model, we need a lot of images for each of the person. And it is of course the drawback of this method. However, this neural token head model allows us to generate the deepfakes even in a single shot manner. It means that now we have only a single image of the target person, and only having the face landmarks, we could animate it even given only a single image. And it means that we're kind of like resolving this drawback of having a lot of images per person. But of course, if you have more images available for a particular person, then the result of the deepfakes can be improved. All right, so now we know a little bit about how the deepfakes are generated. Now let's talk about how we could detect them. Firstly, let's consider the datasets available in this area. As you could see, in the very beginning of the research in this topic, there was a very limited set of available datasets with very limited number of observations in each. That is why it was hard to build any reliable model that could generalize across different datasets and across different deepfakes. However, as the time goes, now there are more and more datasets appearing in this area, and the largest one at the moment is exactly the dataset that came from the deepfake detection challenge that we'll be talking about today. So as you could see here, it contains about 100,000 different videos of the deepfakes, and also a lot of real videos. And another great advantage of this dataset is that it has a lot of subjects, a lot of persons who participated in this video. So it has almost 1,000 different persons, different identities in the dataset. So such large dataset allows us to build more generalizable models, and hopefully this dataset could be used to enhance the research and improve the results of the current models. Before discussing the approaches that are used for deepfake detection that are based on deep learning methods, let's firstly evaluate the human performance on the same task. And it was the goal of the papers that is mentioned here at the bottom of the slide. And the authors of this paper were using again this dataset from the Kaggle competition, and they have collected the videos from there and split them into 5 groups, from the very easy examples where some clear artifacts are seen on the images, on the videos, to the very difficult and difficult examples where it is hard to distinguish between real and fake videos. And they have asked the respondents to say whether they are watching the real or fake video. And here are the results, what they have obtained. So here each bar represents again this group of the complexity from very easy to very difficult, and blue color represents the percentage of people who responded correctly and distinguished the fake video from the real, while the red bars here are for the errors of the people, of the respondents. And as you can see here from this plot, for the difficult and very difficult deepfakes, about 60% to 75% of the respondents are making errors. So it means that it is a very hard problem for the people to distinguish between real and fake content if this deepfake has a good quality. And also, these numbers are probably over-optimistic because people were already aware that they are watching some fake videos, and probably the real numbers are even worse. Yes, there are a lot of different methods to detect the deepfakes in the deep learning, and you could probably find dozens of different papers with different approaches. And we will discuss the most commonly used pipeline in the context of the competition. But for now, I just want to share my personal favorite paper in the area of detecting the deepfakes. And this paper is from 2018, so it is pretty old, and probably all the modern deepfakes could fool this approach. However, the approach is really nice. What we're trying to achieve here is we want to try to detect the blinking in the videos, so whether the person is blinking or not. And the idea here is that for the deepfakes generation, we are usually using this limited set of images per person, and probably the images that are used to generate the deepfakes are all with open eyes. And that is why we want to detect whether the deepfake, the video, is blinking or not. So for this purpose, we're using the general CNN RNN architecture. So firstly, we find the regions of where the eye is located, extract these regions, and pass them through the CNN network for the feature extraction. Afterwards, we use these extracted features in the RNN model. In this case, it is LSTM. And we try to predict the probability whether it is a blinking eye or not. And if, for example, there is a long sequence of the non-blinking person in the video, then probably this video is a deepfake. All right, now let's move on to the competition itself. It is called Kaggle Deepfake Detection Challenge. And it was organized by the Facebook and hosted on Kaggle from December 2019 till March 2020. And the problem was to classify whether a video is a deepfake or not. The metric for this competition was log loss, and the dataset, as we have already seen, consisted of almost 100,000 short clips of 10 seconds each, and 100,000 of them were fake. There were a couple of points that made this competition unique for Kaggle. The first of them was the prize pool. So the prize pool for this competition is $1 million. And beforehand on Kaggle there were some competitions with a similar prize pool, but it is a pretty rare situation on Kaggle. Another property of this competition is that the private leaderboard evaluation was run outside of Kaggle. So participants were providing their pipelines, and then these pipelines were run outside of Kaggle using their Facebook's hardware in order to evaluate the final results. Another point is that the private test dataset dramatically differs from the train and public test datasets. The idea here is that organizers mixed up their private test dataset in a 50-50 manner. The 50% of the dataset was similar to their train and public datasets from the same distribution, while other 50% of the dataset came from so-called videos in the wild, as the organizers told us. And these videos are kind of like just some available publicly deepfakes that are available on the YouTube or on some other platforms, and that could be downloadable. And the models should generalize well not only to our dataset provided to us during the competition, but also they should generalize well to other new types of the deepfakes. And finally, there was also a kind of controversial rules about the allowed external data. So by default, the external data was allowed in this competition. However, both organizers and Kaggle team was answering with a very long delay to what to questions about what datasets are allowed, what licenses could be used, and so on. And that is why, as a result, from the private leaderboard, there were removed a couple of teams from the top 5 of the private leaderboard because they were using some datasets that were against the rules. I have participated in this competition as a part of a team, and our team consists of 3 people, and I've participated together with well-known and bright Kagglers. The first of them is Roman Solovyov, also known as ZF Turbo, and second one is Dmitro Poplavsky. And we have finished in this competition at the 16th place at the private leaderboard, close to the gold zone. Alright, so to dive into the competition, let's start with exploring the dataset that was available in the competition. So here you could see the examples of the original and fake videos of the same video. In the dataset, we have been provided with these short clips of 10 seconds of real and fake videos. And also we had information about the connection, what is their source of the fake video. So if we have some fake video, we had an information what was the original video that was generated, that this fake was generated from. And in this case, you could see pretty easy examples from the dataset, where we have a clear artifact on the face of the person, and it is pretty straightforward to see that it is a deepfake. Another example is here. It is a little bit more better example of the deepfake. In this case, we could see that the generated deepfake is more smooth, and now their quality of the deepfake is much better. However, still the face doesn't look very real. And here is an example of the difficult example in the dataset. So here, as you could see, the deepfake quality is really high with high quality details, and it is really hard for us to distinguish between the original and fake examples in this case. But actually, I have interchanged the order of their videos here, and their fake video is actually on the left, and the real video here on the right. I don't know how many of you have noticed it. But still, the quality of this deepfake is pretty good. So as you could see here, it is hard to distinguish it from the real video. Probably the only disadvantage here is that the light conditions are a bit different in the deepfake generated video compared to the original video. All right, and to generate the deepfakes for the datasets, organizers of the competitions use different methods. And after the competition end, they have shared the paper that is available here at the bottom of the slide, where they have described the whole competition process, starting from the data collection phase towards their evaluation of the submissions and so on. And also they have released the whole dataset on their website together with additional descriptions. However, all this information was not available for us during the competition, so we didn't know what exact methods were used to generate the deepfakes. And in this case, the organizers were using 6 different families of methods. The first one is based on the morphable masked models, where the idea is that we have 2 faces, a source and target, and we detect the landmarks of the faces in both the source and target images, and we try to just cut out the region of, for example, some part of the face from one face and paste it on another face. And as a result, we obtain new faces. But the drawback of this approach is, for example, the artifacts that you could see here, where we could clearly see that the mouse of this person came from another person. That is why the organizers, before applying this model, were searching for the similar faces in their database and applied these models only for the faces that are similar between each other. The second type of the models here in the second row is deepfake autoencoders. So it is exactly autoencoders approach that we have initially considered in the beginning of our talk. And the rest 3 approaches are based on the GANs, and all of them are applying different methods. And the one that we already know about is this here in the pre-last row. It is our neural token head model that we have considered today. And according to the organizers, the best performing model among all these methods was exactly autoencoders. The only drawback here is that, as we have already discussed, we need a lot of images for each of the persons to generate such deepfakes, and also we need to train a single model for each couple of persons. And that is why this approach is very computationally expensive to train for all the possible couples. And among the GAN approaches, the best performing, according to the organizers, was this paper on neural token heads. Also, it is important to mention that this was a kernel competition, so it means that participants were submitting their code, and this code was run in the kernels, in the Kaggle kernels. And that is why there were some limitations that were set in these kernels. First of all, the runtime should be less than 9 hours, and the model size should be less than 1 gigabyte without internet connection. All right, so now we know everything about the competition, and let's talk about what are the approaches that the participants were using to solve this competition. Firstly, let's start with a common data preparation approach. Here we have some input video that is read by the OpenCV library, and afterwards this video we take frames, or independent frames from this video, and afterwards for each frame we could also detect the faces and crop the face regions of the input video. The idea here is that actually the deepfakes are applied only to the face regions of the persons. And that is why it is better to show the model the region of interest where we actually should concentrate on, instead of training the model on the whole frames from the video. And in both of these phases, we could also dump the data to the disk. The idea here is to increase the speed of the processing, the speed of the training, because if we would like to train the model and read the videos on the fly and detect the faces on the fly, it could be a large bottleneck for the data preparation, and it could slow down the training process a lot. And that is why it is a better idea to firstly dump either the frames from the video or their already cropped faces to the disk and read these images from the disk afterwards. The most common face detector that was used in this competition is called MTCNN, which stands for the Multitask Cascade Convolutional Neural Networks. And their implementation that was widely used in the competition is located here in this repo and called FaceNet PyTorch. And in this plot, we could see their performance, the time performance of different implementations of these methods. And of course, we're looking for the fastest performing implementation, because we have this in kernel limitation that it should run under 9 hours. That is why we want the face detector to be as fast as possible, even though there could be some better face detectors that could produce better results, but for the price of their slower speed. Okay, so having prepared the data, now we need to train some models. And again, there were two major approaches that were widely used in this competition. The first one treats each frame as independent image. So in this case, in the trained data, we could extract n frames from the video and treat them as independent images and just train a usual image classification model that is predicting whether their image is fake or not. The drawback of such approach is that we have a single label for the whole video, and that is why all the frames are obtaining the same label. However, there were cases when not all the frames of their videos were modified with a deepfake. And the reason for this could be either some problems with the deepfake generation, or maybe it was done on purpose in order to fool this type of detectors. And that is why such approach has a hard time when we have only a limited set of deepfaked frames. So yeah, and for the inference of this approach, we take each case frame from their input video, and the reason for taking only each case frame is because we don't have enough time in the inference kernel to run the whole video and all the frames through the network. That is why we need to select only subsample of the frames, and afterwards, for each frame, we have our output probability of predicting whether this particular frame is fake or not, and afterwards we have a set of predicted probabilities. And another drawback of this approach is that we need some heuristic or some second-level model that will try to aggregate these individual predictions and produce the final probability of the video being faked. So in this approach is really simple, and it allows us to train just a simple binary image classification problem. The second approach is based on the idea that frames are actually dependent, and we have the video data and we have some temporal component in the dataset. And in this case, we train the model on the sequences of their input frames, and their improvement here is that we just have a single label in this case instead of having separate labels for each independent image. And also during the inference, we are just outputting the single final probability from the sequence of being fake. And usually, the two major approaches are used for this modeling type. The first one is CNN-RNN architecture. In this case, we firstly extract the features using the CNN architectures and pass them to the RNN in order to model the temporal dependency in the frames. And second approach is called three-dimensional CNNs. The idea is we're just using the whole stack of the frames and apply the three-dimensional convolutions to them, and just model them as a usual classification of the three-dimensional data. Okay, so having trained the model, now we need some way to evaluate the model. And in this case, we have two sources of the information. It is our local validation and the public leaderboard. And in the competitions, we're usually trying to mimic the train test split on the local validation as much as possible. And also, we'd like to generate the local validation in such a manner that allows us to get a good correlation between the local validation and publicly reported scores. However, in this particular competition, it was very hard to generate a reliable validation strategy. That is why one of the ideas that we also tried was to find out their different persons in all the videos. It was known that the test dataset contains other persons that are not presented in their trained dataset, and that is why it is better to make a model that is generalizable across different persons. However, in the trained dataset, we didn't have information about what actually the person ID that is located on a particular video. And that is why we manually extracted the faces from all the videos and tried to cluster the persons in these videos. And afterwards, having these person IDs for each video, we could split their initial trained data into the faults using their as a group column this person ID. And the idea was to generate a better local validation. However, this approach has also failed, and it was still very hard to find out the reliable validation strategy. And probably the reason for this has again occurred has been discovered only after the competition end, and it was again described in the paper by the organizers. And they said that actually the test dataset was additionally modified with some additional augmentations, and some of them were just simple horizontal flips or some rotations and changing of the brightness. However, some of them were actually applying some additional face masks to the faces or adding distractors with some other faces in the video. And probably it was the reason why it was very hard to establish a good reliable validation strategy in this competition. And to sum up, here is a slide that combines all the ideas that we have talked so far, and it also represents our final solution. So here is our inference pipeline. We have the input video, and firstly, we split it into individual frames, and we were using 30 frames, 30 uniformly distributed frames through the video. And actually, the majority of the videos have about 10 seconds length and 30 frames per second. So actually, it was about 300 frames per video. And that is why we were actually taking about each tenth of the frames. Afterwards, for each frame, we were using MTCNN model to extract the faces from each frame. And also, we were lowering the thresholds if the face wasn't found on the frame. The idea here is that we don't want to use the lower thresholds in the very beginning, because it will generate a lot of false positive face detections. However, if we haven't found any face on the frame, then we are lowering the threshold in order to find at least one face at the frame. And the idea here is that video at each time point should contain at least one person there in the frame. Afterwards, these frames are passed through their trained models, and overall we had an ensemble of 13 different models, and they represented different families, including dense nets, efficient nets, and as-iris nexts. And afterwards, having these probabilities from the models, we're applying the second level XGBoost model that actually aggregates the individual frame predictions into our final probability. And this final probability was used for our submission. Of course, before converging to this final solution, we have tried a lot of different ideas. And here on the slide, I have summarized some of them, the most promising ones that haven't worked in this competition. The first one is, as we have already discussed, is clustering their actors and the persons in the video to split the validation by the persons. The second idea that we were trying to use is to train a multitask model with an additional semantic segmentation head. The idea here is, instead of using just a single label whether the video is fake or real, we add additional head with a segmentation label where we're showing the model where actually what actual pixels were modified from the real video to the fake. And to generate such labels, we have a real and fake videos, and we just subtract and find the difference between the corresponding frames between the real and fake videos. And here on the right, you could see the example of such a label, where we have mostly a black image and only a lighter region of the face where actually the manipulation was performed in order to generate the deepfake. Another approach that didn't work for us was to obtain the better performance for the efficient net architectures family, because according to the top solutions, majority of them were using efficient nets, and it was their best performing model. However, for us, it was performing good, but not as good as other models, and we were using it only as a part of our ensemble. And also another approach that has failed for us is these CNN-RNN architectures. So we were extracting the features from CNN and then passing them to the LSTM network. And it is similar to this eye-blinking paper that we have mentioned in the very beginning. But again, this approach also failed for this competition. All right, and in the end, let's consider the top winning solutions of this competition and the solutions from the top 5 of the private leaderboard. And we will start with the top 1 solution. So the top 1 solution was treating this problem as a usual image classification. So as our team, it was just taking each frame independently and use standard 2-dimensional CNNs to generate the predictions. For the face detection, it was also using the MTCNN. However, the difference here in the winning solution is that it was using the larger margin around the faces, and it was cropping larger regions around the faces, and probably it allowed to save more information that is passed to the models. Also, the solution was using pretty large input sizes with 380 by 380 pixels, and also was applying some smart augmentations that were based on the face landmarks. And the final ensemble of the winning solution consisted of 7 EfficientNet B7 models. And here are the examples of the augmentations that were applied to the trained dataset. So the idea here is that we firstly detect the landmarks of the faces, and then we're trying to cut out some regions of the faces to make more generalizable. So it kind of adds more regularization to the model, and now the model should look at different parts of the faces in order to detect whether the face is real or fake. The top 3 solution was a bit different. It was using their ensemble of 2-dimensional and 3-dimensional CNNs. However, the underlying model was still EfficientNet B7. This solution was also using a different face detector and applying some different augmentations, and there were some interesting ideas that included mix-up augmentation. This mix-up augmentation was mixing up the real and fake frames from the same video and obtaining the mixed version of these images. And also, this solution was applying the video augmentations on the fly. As we have discussed, it could be very computationally expensive to read the videos and generate augmentations on the fly. That is why these augmentations were applied only to the small crops of the videos. And here are the examples of the mix-up augmentations from this solution. And as you can see here, we have 2 columns, the real and fake examples of the same person, but 2 different videos. And then we are just mixing them up to obtain a new image. And also we're mixing up the target. So, and the target is based on the weights that we're taking the weight of each image. And as you could see here, it produces pretty good results. And it probably also allowed the model to generalize better to the new deepfake types and new faces in the test dataset. And finally, top 5 solution was also similar to the 2 previous ones. It was using the ensemble of 3-dimensional and 2-dimensional CNNs, and was using MTCNN for the face detection. The only difference here is that it was also using the cut mix augmentations. And the idea of the cut mix augmentations is that we are cutting out some regions of the one image and pasting there another part of another image. And so, for example, here in the mix-up we have just a mixed image, and in the cut mix we have different parts of different images. And here is a scheme of the top 5 solution. So actually there were also, as our team were trying different thresholds for their face detection. And afterwards they had two branches for the 3-dimensional models and 2-dimensional models. And also they were applying test time augmentations with horizontal flips to get a better performance of the models. All right. So as I have mentioned, this competition, the private leaderboard evaluation was run outside of Kaggle and was run on the Facebook's hardware. That is why the results of the competition, the private leaderboard, was available only in a couple of weeks after the competition deadline. And once these results were available, you could see the differences between the top 5 public scores and top 5 private scores on the leaderboard. So here is the log loss metric, and you could see that their performance of the private leaderboard has dramatically decreased compared to the initial public leaderboard. And the reason for this is exactly these videos in the wild that were added additionally to the private dataset. And the the organizers of the competition, in their paper, they have also split these final metrics into two. The first one is the log loss based on the videos that are similar to the initial dataset. And as you can see here, these numbers are pretty much correspond to the public scores. And the second part is their performance on the new videos. These new videos from the wild, from the YouTube and so on. And as you can see here, the difference in the performance is really huge between these two groups of videos. And log loss is probably not a very good metric to interpret, and that is why here are the plots of the ROC-AUC metric for these two groups of videos. And for the similar dataset, for the similar videos on the trained dataset, we could see that the performance on the private leaderboard was almost perfect. So we have ROC-AUC of 0.98 in the top 5 solutions. However, the performance on the new videos, on these videos in the wild, is much worse. And their ROC-AUC scores in this case is only about 0.7. And probably these plots are a nice way to make a conclusion and to conclude our talk today. The conclusion here is that now it is pretty easy to build a model that could detect the deepfakes and could produce a very good result on the provided dataset. However, it is still very hard to build a model that generalizes pretty well across different datasets and across different types of deepfakes. And that is why we could expect a lot of research and a lot of room of improvement in this area in order to improve their quality of their deepfake detections. So that's it. Thank you very much for your attention, and I'm happy to answer all of your questions.